Okay, guys, so today we're going to continue with regression topics, um, and but it's a little bit different, and it's going to require a little bit more mathematics than linear regression. We're going to talk about what's called logistic regression. Okay, so all right, so let's start with a motivating example. So suppose we want to predict um, whether or not um, a student will be admitted to university, let's call it like A or something, um, based off of their GMAT score and their GPA. Okay. So here we're missing parts of the application, right? So the GMAT score and their GPA is just one part of many pieces of an application to a university, such as your application letter, right? Your reference letters, right? So this is not going to ever be able to definitely say whether or not a student will be admitted. But what we can do is we can seek a likelihood that a student will be either admitted or not admitted, right? So for this example, this is going to be a binary decision, right? Either admitted or not admitted to the university, okay? And what we're going to be training our model to find is a way to predict a probability that a student will be admitted to this university. Okay, so with that being said, I'm going to slowly start the transition into neural networks from here on out. So with that in mind, I suppose that we're going to try to model logistic regression as a very simple neural network. And there's a few components of this. So let's start with, so feed forward. Okay, and this is with a single neuron. Okay, so suppose for this example here that we have n data points. So we have x1, y1, dot, 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 to xn, y. Right? Okay, so here our feature vectors are going to consist of a previous student's GMAT score and their GPA. So it's a two-dimensional vector for x. And then y is going to be either a 0 or a 1. So x of I is something like student I GMAT score and student I GPA. And then y sub I is just an element of the set 0, 1, where 1 indicates student I was accepted to University A. 0 if not. Okay, so we have a feature vector and a label for each of these data points. So this is, again, a supervised learning situation. And we wish to predict either a 0 or 1. And the way that we're going to do that is by assigning a probability given a feature vector. And if that feature vector is greater than 0.5, then we'll assign a 1. If that feature vector if we predict a probability less than 0.5, then we'll assign it a 0. Okay, so we're going to use this data to train on, and then hopefully that would be able to help us predict in the future. So in order to get out of prediction, for a given feature vector xi, we're going to envision this as a single neuron. Okay, so we have 2 features for each vector. So it would be like xi first feature, which is the GMAT score. And then we have student I, the GPA. And then we also have the bias, which we're going to feed in as a 1. Okay? And then here we'll have a weight 1, a weight 2, and then a bias B. And we can consider this a weight as well, but for today's lecture, we're going to go ahead and say that we'll call it B and call that W. And what we're going to do here is we're going to say that as the input to this neuron, we have Z. And what is Z? Z is just a linear combination of these values. X1 times W1, X2 times W2, 1 times B. And you add those all together, so what that will look like is W transpose times Xi. So I should call this I. This is for a given prediction. For a given feature vector I, we have a Zi as our linear combination. Okay, so it's very important that you know that the input Z is a linear combination of the weights and the feature vector for I. Okay? Now, this value is not going to be a probability, right? This value can range from negative infinity to positive infinity based off of the varying weights and biases you pick, right? However, if there are ways to squish this thing, this quantity, this is a number, right? Squish this number into a value between 0 and 1. And the way that we're going to do that is by using what's called the sigmoid function. And that is going to give us our prediction for the ith input. We'll call that y hat I. And y hat I is the sigmoid function applied to zi. Okay. Now, what is the sigmoid function? The sigmoid function is so sigmoid of x is 1 divided by 1 plus e to the minus x. And if you plot this function in the xy plane, you see that this is 0.5 and this is 1, right? It looks like this. Kind of has like an S shape to it. But all the values are squeezed between 0 and 1 for all the real number lines. So this is going to give us what we're going to interpret as a probability. So, and just to like reiterate for your notes maybe, this is sigmoid applied to W transpose times xi plus b, which is the same thing as saying 1 over 1 plus e to the power of negative W transpose times xi plus b. Okay? So, what this ends up giving us here is that for a given I, a given feature vector I, we feed the features into the neuron, take a linear combination of those features as z, and then we choose a function after the fact to feed that linear combination into to get a hypothesis, an output. So y hat here is our hypothesis for feature vector xi. It's a prediction, right? It's not necessarily a prediction yet, it's a probability. So really I should say that this implies a hypothesis because it's a probability, and if that probability is high enough, we can say that it's going to be a 1, and if it's low enough, we can just say that it's a 0. So it does imply a hypothesis or a prediction for x of I. Okay, so we're calling this feed forward right now. Now, it might not make sense why we're calling it feed forward yet, but the basic principle is that we have feature vectors, linear combination, apply an activation function of our choice, get output. So we have take one of these things up here, one of these data points, feed in the features, get out the probability. Take another one, feed in, get out something else. Take another one, feed in, get out something else. Now, just as a reason why I'm doing this is that soon we're going to start stacking these things, these neurons together, and we'll be feeding forward for a while, and not just in one step. Okay. Okay. So keep in mind that z is that, y hat for a given input I is that, and the sigmoid function looks like that. And we're feeding in for a given entry. Okay? I'll give you a second to write that down. Just make sure that you have that sort of this mental image in your head. And there's capital N data points in our training data set. Okay? Okay. So I'm going to draw that neuron again up here just so we can keep in the back of our minds what's going on. So give me a second to draw this real fast. Let's see. Okay, so we have part one of building our neural network. It's built, it's done. So now we need to consider the next step, which is coming up with a loss function. So the next step is to come up with a loss function. And the idea that we're working with here is that we have a way to predict a probability that's based off of the weights and the bias. So our next goal is to write a function in terms of the weights and the bias that if we minimize, makes the predictions, the hypothesis that we make, makes them better on the training data set. So our goal is to write a loss function in terms of the weights and biases that if we minimize, we'll be minimizing according to this being close to the actual desired output. And by that, I mean, we want something like, so we want something like a loss function that compares y hat to y for a given input, I, and it's superscript I there, right? It somehow measures how close y hats of I is to y I. That's what we want. Design a loss function that does this. So in order to derive such a thing, first consider maximizing P of y given x, so P superscript I given P. So probability of label yi given features xi. So this is the probability that y hat is equal to y I. So the probability that these are close together, right? So remember, y hat, so this is, I shouldn't write this equal sign, that the probability that, say, y hat I predicts y I. Currently, y hat I is a numeric value, but we can say that something like the prediction is something like 1 if y hat I is greater than or equal to 0.5 and 0 otherwise. Something like that. So in this probability space, there are only two discrete outputs. There's either 0 or 1, right? So, so I can say maybe like, since there are only two discrete outputs in this probability space, right? Like think about flipping a coin. This is, say, maybe subject to the following formula by renewing. So we have a, so probability of y I given xi is equal to, so this is like our p, y hat. I'm going to drop the superscript for now. It's just going to get messy. And this is y hat to the power y times 1 minus y hat to the power 1 minus y. Okay, so again, y hat is the probability, or the label, I mean, so the expectation of it, right? And we just plug into Bernoulli's formula here for these spaces. Okay, so now that I have that done, I'm going to have to erase all this, and we're going to derive the loss function now. Okay, so again, just starting from up here, probability. So I'm going to drop the superscripts because it's going to take too long, but just know that this is for a single given entry. So the probability of y given x is equal to y hat to the power y times 1 minus y hat 1 minus y. Now, what we want to do is we want to maximize this probability, right? We want this to be correct. We want the correct output. So what we're going to do that is not going to hurt anything is we can take a logarithm on both sides. So take the log on both sides. Okay, so log on both sides. So maximizing this quantity here is the same thing as, or is equivalent to maximizing this log function here. They should have both the same argmin and max, or argmax. So now let's use our rules for logarithms here. We see that the product here is going to give us a sum of logarithms, and then the exponents can all become coefficients by the properties of logarithms. So we have y times log of y hat plus 1 minus y of log of 1 minus log hat. I mean y hat. Okay. Now, but what we want to use is we want a minimization problem, right? So we're like, we want to maximize this, but for our algorithm, for our gradient descent, we want a minimization problem. So we can just multiply both sides of this by -1, and then we want a minimization problem. Right, maximizing this is equivalent to minimizing the negative of it. So we just do that. Okay, and I want to minimize this. Okay, so this right here is called a cross entropy loss function. Okay. And we'll define it to be, so use the notation loss cross entropy of y hat y is equal to -log probability of y given x. Okay. So this right-hand side is really what we're going to be working with, because all of this we can rewrite as just replace the y hat by what it really is, sigma of z, or the sigmoid applied to z. Like that. And finally, if we replace z by what we want, by z by its linear combination form, we'll have the final thing that we want to. So notice, like, where is that? This version right here is in terms of y and y hat, right? You see that. So that's what this notation is denoting. It's -log py of x. Keep that in mind, -log the probability of y given x is the cross entropy loss of y hat and y, and notice there's only y's there, right? But now if I go one more step here, I get that this is y log of sigma of w transpose x plus b plus 1 minus y log 1 minus w transpose x plus b. So this here is going to be the loss, but now cross entropy in terms of W, B, what notation we end up using? Yeah, W and B. Now we can write this in terms of WB, and that's the thing that we want to minimize. This quantity here. Okay. Okay. So take a minute to make sure you've written that down before I move on. Yeah. Okay, so here is our feed-forward network, and then, so this is like part one of our model. Part two of our model is our loss function. This is going to be cross entropy. So loss cross entropy of WB. See if I can squeeze it up here. So minus y times log sigma W transpose x plus b plus 1 minus y times log of 1 minus sigmoid applied to W transpose x plus b. Okay, so we have a loss function now. So next part, or 3, is to train. And what we're going to use at first is stochastic gradient descent. Now, this is also well, yeah, we don't need back propagation yet. Yes, there is no back propagation. But yeah, we're going to train using stochastic gradient descent. So what we want, theta hat equal to arg min over theta of the cross entropy loss function with respect to x, y, semicolon, theta, where theta is equal to W comma B. So we want the minimum possible loss function over all W and B. That's what we want to solve. Okay. Now we're running out of time. I was hoping that I'd be able to show you the derivation of this, but I guess I'll leave that to you, or maybe I'll just show another video finding this. But if we look at the partial derivative of the cross entropy loss with respect to the J component of W, recall W is going to have 2 entries right now, right? For a given W and B, this is going to turn out to be actually not so bad it's going to turn out to be, what is it? It's going to be sigma wx plus b minus y times xj. This is actually not hard to derive if you just look at this thing and you remember how to take derivatives of logarithms, and then look at the derivative of the sigma, the chain rule applied to sigma with respect to w. And then in a similar fashion, the partial derivative of the cross entropy loss with respect to b, it's going to be, notice the xj comes from the jth component of w times the jth component of x in that dot product. Here, there's no coefficient of b, so it's just going to be the inside there. Yeah. Okay, so what this gives us all the information we need to find the gradient now. So what we're going to say is that for a given data point xi, y, wj is going to be equal to wj minus alpha times this business here. So this is like k plus 1, k plus 1, no, just k. This is just k for at the kth iteration of our step. And this is for j equals 1, to I don't know. I'll keep it for our example here for j equals 1 and 2. W is only going to have two components. This is a k right there. And then finally, there's only one b. So b k plus 1 is equal to b k minus alpha. Our learning rate, as we recall from linear regression, the partial derivative of the cost of the loss function with respect to the phi. This is again like that. So the first way that we can do this is by the stochastic gradient descent. We randomly pick a point of data, and then we calculate the gradient according to these rules here, and we can update with the partial derivatives or the full gradient if you want to use vectors. The weights and the biases, after we initialize them both to be 0 or some small random number. And then we iterate this until we see that the cross entropy loss is decreasing sufficiently. Okay. So the k's here represents the kth iteration. The superscript here just represents the ith data point. The j's here just represent either feature 1 or feature 2 from vector I. And then if you iterate this, you should get some type of results to work with. Okay. So I'm afraid I don't have time to actually program this from scratch with you today. So what I would suggest you do on your own before next class is to go to Blackboard and pick up this candidates data set. And then you see here that you can read this in, and we have GMAT, GPA, work experience, and then the admitted column here. So something like, like X data would be equal to the list of tuples X for X in zip. What did I call it up here? Data, GMAT, GPA. Data dot GMAT, comma, data dot GPA. And then Y data equals X for X in data dot admitted. All right, so we have that business there. So you can read this in and then define your loss function. By the way, you can just type log in Julia, it's fine. So I guess like for a given point xy maybe. So loss cross entropy or cross entropy loss, or I don't know, loss, whatever. For a given ith entry, and like this, like the features, labels, weights, biases. And then just go ahead and start trying to figure out how to program this. I don't think I'm gonna go and waste this. We won't have enough time to do it, but next time we'll do it. So I guess today was just kind of like the theory and derivation of logistic regression, and then next time we'll go ahead and program it. But I highly encourage all of you to go ahead and start trying to program this and see if you can get it to correctly predict if a student will be accepted or not using that data set that I gave you. All right, so that'll be it for today. Hope everyone stays safe, and I will see you next week.